What does it actually take to rigorously design a plate and frame heat exchanger? It is not simply a matter of entering two temperatures into Aspen EDR and clicking the design button. In this tutorial, we are going one step further. We will start with a water ethanol heat exchanger system, design the individual plate, specify its geometry, and then use Aspen EDR to develop the complete plate and frame heat exchanger. So if you want to understand not just how to use Aspen EDR, but how an engineer approaches the rigorous design of a plate and frame heat exchanger, this video is for you. Hello everyone and welcome back to Chemical Engineering at Aspen channel. I am Dr. Muhammad Haris Humayun and in today's tutorial we are going to perform a rigorous design of a plate and frame heat exchanger using Aspen Exchanger Design and Rating, or we can call it as Aspen EDR. Unlike a basic heat exchanger simulation, this tutorial focuses on the actual plate design and exchanger geometry along with the thermal and hydraulic requirements of the system. The important point in this tutorial is that we are not treating the heat exchanger as a black box. We will look at the design from the perspective of the individual heat transfer plate and then see how these plates come together to form the complete exchanger. We will also examine important design parameters such as chevron angle, plate thickness, plate pitch, pore diameter, heat transfer area, pressure drop, and many more. This makes the tutorial particularly useful for anyone interested in heat exchanger design, process equipment design, and Aspen EDR. Let's begin with the process specification. Our system consists of water on the hot side and ethanol on the cold side. For the hot water stream, the inlet temperature is 65.6 degrees Celsius and the required outlet temperature is 29.4 degrees Celsius. The operating pressure specified for the hot stream is 0.18 bar. For the cold stream, the flow rate is 31.5 kgs per second. The ethanol enters at 23.8 degrees Celsius and leaves at 46.1 degrees Celsius with an operating pressure of 2.07 bar. These are the process conditions provided for our heat exchanger design. There are two more important design constraints. The allowable pressure drop is 0.07 bar and the specified fouling resistance is 0.0003 square meter Kelvin per watt. These constraints are particularly important because a heat exchanger is not considered properly designed simply because it achieves the required heat transfer. We also need to make sure that the hydraulic requirements are also satisfied. Now coming to the interesting part, before designing the heat exchanger, we need to define the characteristics of the heat transfer plate. The plate geometry has a direct influence on both heat transfer and pressure drop. One of the important parameters is Chevron angle, which influences the inflow path and hydraulic resistance and is given as 65 degrees. We also have horizontal port center distance of 650 millimeters and a vertical port center distance of 2600 millimeters. The plate thickness is 0.6 millimeter and this plate thickness affects the mechanical characteristics of the plate. The compressed plate pitch is 5.28 millimeter and this plate pitch determines the channel dimensions. The pore diameter is 400 millimeter and it influences how the fluid enter, distribute through and leaves the exchanger. So when we change the plate geometry, we are not simply changing the appearance of the exchanger, we are changing its thermal and hydraulic behavior. This is why rigorous design requires us to consider both aspects simultaneously. So now let's move to Aspen EDR and design this complete process. So here we will click on this new first, we will select the plate and we will create it. And the first step is to establish the two process stream. As we know, our hot stream is water, while our cold stream is ethanol. So we have been given the plate material as SS304, which we will take it over here. We will go to the problem definition. We will specify the process data. First thing is to convert it into the SI units. And we have been given the information that the cold stream has a mass flow rate of 31.5 kg per second. The inlet temperature of the hot stream is 65.6 degrees centigrade, while that of the outlet temperature is 29.4 degrees centigrade. The inlet temperature for the cold stream is 23.8, while the outlet temperature is 46.1 degrees centigrade. Thus, operating pressure for hot side is 0.18 bar, while that of cold side is 2.07 bar. Now, the allowable pressure drop for both sides is 0.07 bar, and the fouling resistance for them is 0.0003 square meter per Kelvin per watt. So this is our first part which we have done it. Now we will go to this physical property data. In hot stream compositions. We will specify, or we will use BJAC, and the hot side is water as has been given to us. So we will click on this water, we will add it, and it is okay, and you can see the composition is 1. For cold stream, we will again use BJAC, and in search data bank we will select ethanol because ethanol is at hot side, at cold side, and it has been specified as 1. So now our next part is to specify the plate conditions or plate size information. In calculation mode, we will first give it to design given plate, and now we have been given the chevron angle and the different information. So 65 degree centigrade is the chevron angle, and all these informations are given to us in millimeters, that the horizontal port distance center is 650, the vertical port distance is 2600 millimeter, plate thickness 0.6 millimeter, compressed plate 5.28 millimeter, and port diameter is 400 millimeters. So now everything is now specified over here. We have specified the plate material. We have given the information about the size. We have also mentioned that we want to design a given plate. We have entered the process data. We have given the compositions of both hot and cold sides. So now we will click on this run button to get our required results. And you can see that the results have now been achieved, and there is no warning in the system. All of the heat is transferred from hot side to the cold side to reach to the required temperature. Now we will look at the things one by one. The optimization path, only one design has been checked and that has been found to be satisfactory. Recap of design, these informations, the API sheet has been given to us. So you can see the hot side, cold side information has been given to us. We were not given the information about the hot side flow rate, so it has been computed by Aspen, and it is 0.7228 kgs per second. If we go to the thermal hydraulic summary, the performance information is given to us, the heat transfer information, the pressure drop information, and we have used the plate method to analyze it. In exchanger geometry, again the same information which we have discussed earlier. Thermal conductivity, effective surface area is 386.7 square meter, plate pack weight is given to us. Similarly, if we go to this exchanger diagram, because this is important part, that the stream 1 enters at 65.6 degrees centigrade, while it leaves at 29.4 degrees centigrade. The stream 2 enters at 23.8 degrees centigrade, while it leaves at 46.1 degrees centigrade. There are 141 plates in the system. This is the horizontal port center which we have specified, that is 650 millimeter, while that is the vertical port center which is 2600 millimeter, and the plate flow width is calculated, which is 1070 millimeter in the system. The chevron angle we specified it, pore diameter we specified it, plate thickness we have specified it. And coming to the last part, which is the cost and its weight, you can see The empty plate pack weight is approximately 1870 kgs, while the plate pack weight with water is 4126 kilograms. These results demonstrate another advantage of using a detailed equipment design tool. Similarly, the total cost is 33875 dollars. So we are not only obtaining the thermal performance, we are also obtaining information that can support equipment selection, engineering evaluation, and preliminary economic assessment. The key lesson from this tutorial is simple. Heat exchanger design is not just about calculating the heat duty. A successful engineering design requires us to consider the process conditions, the properties of the fluid, plate geometry, heat transfer area, pressure drop, and equipment configurations all together. And Aspen EDR provides a powerful environment for bringing all of these aspects together. If you found this tutorial useful, please like the video and subscribe to Chemical Engineering and Aspen channel. And I would especially like to hear from you in the comments what heat exchanger should be rigorously designed next. Shell tube, air cooler, double pipe, or another type of plate and frame heat exchanger. Let me know your suggestion in the comments. And if you want more practical tutorials on Aspen EDR, Aspen Plus, HISIS, process simulation, equipment design, and chemical engineering, make sure you subscribe to the channel. Thank you for watching, and I will see you in the next tutorial.